We now have our first Maxwell equation in integral form, or Gauss's law. The right-hand side signifies the amount of charge inside our Gaussian surface. Although Maxwell's equation is written as though there's only a volume charge density, it's the total charge enclosed, so you could have a volume charge density, or surface charge density, or line charge density, or point charges, or any combination of the four. So the right-hand side is really implying all these different types of charges you might have inside your Gaussian surface. A school of thought on how to teach electromagnetics is that you should just be presented Maxwell's equations and how to do the vector calculus, and then you utilize these equations. I think it is much better if you have a conceptual understanding of these equations, that you have a mental model from which these equations make sense and they're not just mathematical abstractions. D represents our electric flux density. If we integrate d dot ds over some closed surface, we will get the amount of electric flux that is leaving that closed surface. Electric flux begins on positive charge and terminates on negative charge. So the amount of electric flux leaving a volume is equal to the total charge inside that volume. From your mental representation, then, you can just write down Gauss's law. Maxwell's equations are not equations that are derived. They describe physical observations. These four basic equations are all you need to describe anything dealing with electromagnetics. You might ask, where is Coulomb's law? Well, you can derive Coulomb's law from Gauss's law. Let's apply Gauss's law to a point charge at the origin. A point has spherical symmetry, so a point charge will have an electric field intensity that's only in the radial direction and will only depend on the spherical component r. With point charges in free space, there really is no difference between the electric flux density field and the electric field intensity. There's just this multiplicative constant of epsilon sub 0. So an alternative way to write Gauss's law is as the integral of E dot ds over a closed surface is equal to the charge enclosed divided by the permittivity of free space. Now let's substitute our form for the electric field intensity for our point charge Q at the origin. And now we'll choose a Gaussian surface that is a sphere centered on the origin so that the electric field intensity is constant everywhere on the surface of that sphere. Here we have our Gaussian surface, and we can take the magnitude of the electric field intensity to the left of the integral. The unit vector dotted with our differential surface will give us the differential surface in the radial direction. The integral of the surface differential in the radial direction over a sphere of radius r is just the surface area of that sphere, or 4 pi r squared. So now let's solve for the magnitude of our electric field intensity. And if we add the unit vector in the r direction, we will have our electric field intensity for a point charge at the origin. And here is our electric field intensity for our point charge at the origin. Let's place a second charge, q sub t, at position vector r. The force on q sub t due to our electric field intensity is just q sub t times the electric field intensity. So now let's substitute in our electric field intensity. And the result is Coulomb's law for the force on Q sub t due to the charge Q.